Bismillah ar-Rahman ar-Rahim. I'm Dr. Farhad Ali, your instructor for the course of Theory of Fluid. I hope you will have this lecture in very good health. This lecture includes the forces experienced by the fluid particle, and we will also discuss this, that how uh, some of these forces develop stresses, and then while using the same stresses we will try to derive momentum equation for any fluid, for the Newtonian fluid or for the non-Newtonian fluid. So uh, we will try to cover these topics in today's lecture. In our study of fluid mechanics, we will need to understand what kind of forces act on the fluid particles. This is very important. Okay, we have to know that what kind of forces act on the fluid particles. Each fluid particles can experience two kind of forces. One is surface forces, and the second one is body forces. So remember, each fluid particle can experience these forces: surface forces and body forces. What are surface forces, or what is surface force? Surface forces include all forces acting on the boundaries of medium through direct contact. Okay, these are the forces acting on the boundaries of medium through direct contact. These forces are generated by contact with other particles or solid surface. So these forces can be generated when one particle is contact with other particles. These are the internal forces. Okay, or it may be that it is in between the solid surface and the particle. Example of such forces are pressure and stresses. These are the example of the surface forces. If you recall your memory, we have already discussed this, the difference between stresses and pressure, that while when the fluid is at rest, it experiences pressure, there will be pressure, but the stresses will be zero. And when the fluid starts flow, then there generates stresses. So stresses develops while the fluid is moving. Okay, so these are the surface forces. These are very important because of this stresses are produced, and we will further discuss stresses. Okay, the second force which is experienced by The second kind of force which is experienced by the fluid particles is the body force or body forces. Force is developed without physical contact. Look at the difference between these two. These forces, surface forces, develop due to the direct contact with the fluid surface, and the body forces develop without physical contact and distributed throughout the volume of the fluid, or you can say uniformly distributed throughout the volume of fluid. When you have a fluid in a region, so in the all region, this force will be uniformly distributed. Its amount everywhere will be same, and such forces are called body forces. Examples of body forces are gravitational and electromagnetic forces. Okay, these are the gravitational force, okay, and electromagnetic forces, magnetohydrodynamic forces are the examples of the body forces. For example, if the fluid is electrically conducting, so in the whole fluid, this force will be uniformly distributed. Okay, similarly, gravitational fluid, if you have in a region of, okay, the region occupies the fluid, so in every particle, the amount of the gravitational force will be same. The gravitational body force acting on an element of volume dV is rho g dV. This is the gravitational body force acting on an element of volume. Okay, if the element has this volume dV, so what will be the gravitational force? The gravitational force will be rho g dV, where rho is the density, mass per unit volume, and g is the local gravitational acceleration. Thus, gravitational body force per unit volume is gravitational body force per unit volume is rho g. Rho g is per unit volume. The gravitational force, the gravitational body force per unit volume is rho g, and the gravitational body force per unit mass is only g. So these are the two forces, and you will see, we will consider, because uh, the stresses, because we will study the force, the fluid in motion. So when we say that the fluid in motion, we are studying the fluid dynamics. So we study the fluid in motion. So we will experience, or we will face or study the stresses. Okay, and stresses are the surface forces. But at the same time, for example, if the force is electrically conducting, so gravitational force or magnetohydrodynamic force will be applied uniformly to the fluid, and we will also, that is called body force. So actually the force, just like in uh, the force is applied on the fluid particle according to Newton's second law of motion, F is equal to ma. So F is equal to means if that force will be consist of surface force and body force. So that F will be the sum of surface force plus body force. The surface forces will generate stresses, okay, the surface stresses. And from these stresses, we will derive the momentum equation, the governing equation, and plus there will be some body forces. Okay, so after the surface forces, now we are in the position to study the surface stresses. Surface stress. Surface forces on fluid particle lead to stresses. Surface forces on fluid particles, the forces which have direct contact with the fluid surface, and such forces are not uniformly distributed. So surface forces on fluid particle lead to stresses, and we will explain this, support this sentence from the schematic diagram or the pictorial, okay, from the pictorial representation, that how the force acting on an infinitesimally small unit area and how it generates stresses. The concept of stress is useful for describing how force is acting on the boundaries of a medium, that is fluid or solid. Okay, so why we study stresses? So the concept of stress is useful for describing how force is acting on the boundaries of a medium, and that medium may be fluid or solid. That how forces acting on the boundaries of a medium are transmitted throughout the medium. The stresses in a fluid are mostly generated by motion rather than by deflection. We have already discussed this, that stresses in a fluid are mostly generated by the motion. If you remember the viscosity, that viscosity is the properties of a fluid, while elasticity is the property of a solid. So why deflection? So there will be no deflection. That is why, rather than by deflection, deflection occurs in solids. So in fluids, stresses are mostly generated by motion, and you know that while the fluid is moving, so the viscosity resists the flow, and at the same time you will see that the stresses develop. Imagine the surface of a fluid particle and contact with the other fluid particles. Okay, let me take that the surface of a fluid, one fluid particle in contact with the other fluid particles. Consider the contact force being generated between the particles, as we have one particle, there is another particle, and there are forces generated between the two particles. Consider a very infinitesimal small portion, say del A. So this is very small area of the surface at some point C. We consider this point C, and at this point we consider this area, very infinitesimal area del A. And as the area is infinitesimal, so the very infinitesimal small force del F acting on a this area, small area, and as this force is vector, so it may be resolved. Let it be resolved in the 2D into two components, one normal to and the other is tangent to the area. So because if this vector force, this may be divided as resolved as normal to the area and tangential to the area. So this force will be resolved into two forces, Ft, and we call this Fn. So Fn means that force which is normal to the area, and the other force which is tangential to the area. A normal stress sigma n and a shear stress tau n are then defined as, because using these forces, as these are the surface forces, it will generate the stresses. Okay, so you can see this, and we have already discussed this, that stresses are nothing but these are the forces per unit area. So as we have considered the small infinitesimal area, you can see from this figure. Okay, let me first discuss this figure. Okay, this is a point C, and we have considered the small area of del A, and this force is applied on this area, a very small force del F is. Now we have resolved this del F force, you can see, resolved this forces into normal to this area. Look at this is normal to this area, okay, and this is tangential to the area. So we denoted this by del F T, and this is del F N. Okay, so maybe look at this one. This is the area. So okay, this is just like normal. So I don't know, I cannot show this, but this will be like this. Okay, you can see that it will be normal. So it means normal will be in this direction. So in the 2D I can just show normal as this, and this will be the tangential parallel to the, this is normal to this area. You know that how will be the normal position. Okay, practically when you physically show what will be normal, and this is tangential, and this is the vector force F. So this force F has been resolved in this one, normal Fn and Ft tangential. So now this force per unit area, this is del A. When it applies on this area del A, what we call this, when force is applied on the area, so Fn del A, because we have two forces, and Ft del A divided by del A, force per unit area. So forces are different, area is same. Okay, as this is the normal force, normal to the area, so we call this normal stresses. This is how the stresses develop, like this. So when force is acting on area, so it generates actually the stresses. Just like in the fluid flow, viscosity applying forces on the fluid particles are two particles. Look at this, these are the two particles, and these two, the force is generated between these two particles. So as the force is generated in these two particles, this force develops stresses, and if this is this force is normal to the area, so it will be the normal stresses. If it is tangential to the area, so this force will be denoted by, from the, sometimes we denote it from tau, the tangential stress, or sigma t. Also we can denote this from sigma t, tangential, sorry, not in, tangential stress and normal stress. So this is actually uh, what we have shown in the text. So it is supported by this factorial representation. Okay, and now again you can see this is in the orthogonal coordinates. In the orthogonal coordinates, this is actually orthogonal coordinates. Okay, and when the orthogonal coordinates are transformed to the Cartesian coordinates, in this you can see only the normal and tangential, but in this case we have the Cartesian coordinate x, y and z. So the force is resolved into three forces: the surface, if this, and we have three perpendicular planes in three mutually perpendicular surfaces. So first, for example, if you consider the x surface, then we have the y surface and then z surface. So if we consider the x surface and the force is outward normal in the x direction, so we say that this is a normal force, and the force which is in y direction but the plane is x, so we call this tangential. So these two forces, z force and y force, in the case of the x plane will be considered as tangential forces, while the force in the x plane in the x direction will be considered as a normal force. And how these forces then generate stresses. Okay, so you can see, let me take this as a x surface, which I have already discussed in the previous lectures, that if we consider three perpendicular surfaces in the cube form, look at this one, sorry, so I don't have a proper hold on this marker, so the graph will be not fair but just rough graph. And now you can see this is your x-axis, this will be your y-axis, and this will be your z-axis. Okay, so now you can see the three surfaces. This is called the x surface. We call this x surface. Okay, and this is called the y surface similarly, and this is called the z surface. So now when we force applied on this surface, So its direction will be in x direction. This will be Fx. The force will be applied in y direction. So that will be Fy. And the force will be applied also in this direction, which is called Fz. So now the force per unit area, this area, where this area is now Ax. Let me denote now del Ax. Del Ax. The whole area is now this del X. So first the force which is in x direction, and the area is also x, the plane is x plane. So what is this? Actually this is nothing but stresses, but this stresses, as this is in the x plane in x direction, so this x will be considered as a normal, and we will consider this stress which develops will be normal stress. But look at this one, the force which is acting in y direction. The force is in the y direction on the small area del a y, del ay. The force is also del, okay, small forces. This is also small force. So now look at this one, y direction, but the plane, sorry, it is x. The same plane I have considered. Del a x. So the force per unit area, and the plane is x. So now this force, as the plane is x, but the direction is not in x but in y, so we will consider this force as a tangential force. So when the tangential force acting on the area, so that this will be considered as a x plane in y direction. We call this shear stresses, tangential stresses. Similarly, look at this force Fz. Again, it is acting on the same plane. This is a very small force del Fz, but acting on the area del Ax, which is equal to, again, this is in the z direction. So the plane is not z, the plane is x. So this force will be considered as a tangential force. The tangential force per unit this area, which is x plane. So this will be also considered as ta x plane, but in z direction. So in one surface we have three stresses. One is normal and two is tangential. Similarly on this one will be, the force will be acting in this direction. So now you can see this is the x y plane in y direction. Okay, so look at this one. On the y-x plane, you will have these three stresses: sigma x-axis, ta xy, and ta xz. Similarly, for the y plane, this will be sigma yy, and this will be ta yx, y plane in x direction, and ta yz, y plane in z direction. And similarly for the z plane, because there are three perpendicular surfaces, one, two, three. Okay, so let me come to the point where we have left the discussion. So I think, okay, here. So the force, very small force F acting on a very small area, may be resolved into two components. One is called normal to the surface force, and the other is tangential to the area, normal force to the area, tangential force to the area. Okay, so the stress which is produced, force per unit area produces stresses. So this stress will be considered as a normal stress, but this force will be considered as a tangential force. Subscript subscript n, the stress is included as reminder. It gives you reminder that the stresses are associated with the surface del A through point C having an outward normal in the n direction. The fluid is actually a continuum, so we could have imagined breaking it up any number of different ways into fluid particles around point C, and therefore obtain any number of different stresses at point C. So as you know this from a single point, uh, many planes can be drawn, infinite planes can be drawn in dealing with vector quantities. Dealing with vector quantities such as force, we usually consider components in an orthogonal coordinate system. I have already discussed orthogonal coordinate system. In rectangular coordinates, we might consider the stresses acting on a planes. In this, we consider the and tangential normal and tangential coordinates. The force which is acting normal are in tangent to the plane. But in rectangular coordinates, we might consider the stresses acting on a planes whose outward drawn normal are in the x, y, and z direction. If the surface is x, so the force which is acting in x direction will be considered as a normal. If the surface is y and the force is acting in y direction, so it will be considered as a normal. And similarly for z. As we have shown in the figure 2, we consider the stresses on the element. This is the element having this area whose outward normal is in the x direction. So I have already discussed these things. Okay, so I have and then we look at this one. Okay, I have already do this. Now taking limit del x tends to 0, because this will show you that you are studying something on the point, and from the point we can discuss, or we can apply the calculus. So you will have this dfx by dx. And similarly on this is actually x plane in x direction, so that's why we have considered this as a normal stresses. X plane in y direction, I have already discussed this in this area. Okay, I have already discussed this is the same. So fx by x, these are the x shear stress in x plane in y direction, and this is the x plane in z direction. Okay, so we have used double subscript 1, 2, double to label the stresses. The first subscript, in this case x, indicates the x plane on which the stress acts. In this case, the surface perpendicular to x-axis. The second subscript indicates the direction, like x direction, y direction, and z direction. The second indicates the direction in which the stress acts. Consideration of the area element del Ax would lead to the definition of stresses sigma xx, tau ix, and tau zx. Use of the area element del X would similarly lead to the definitions of, again, sigma x, tau ix, and tau zx. Okay, although we just look at the three orthogonal planes, they are the three orthogonal planes perpendicular to each other, three planes. An infinite number of planes can be passed through point C. As I have mentioned this before, that infinite number of planes can be passed through point C, and the infinite number of stresses will be produced, resulting in infinite number of stresses. associated with the plants through the point. But fortunately, look at this, is we are very fortunately the state to describe the stresses at a point can be described completely by specifying the stresses acting on any three mutually perpendicular planes. So if we find the stresses on the perpendicularly three planes which are mutually perpendicular, so these forces are enough, and the complete stresses can be described from these uh, three perpendicular planes. The stress at a point is specified by nine components, and you can see here nine components, because look at this one, we have one, two, three. This is only for the x surface. Now for the y surface, there will be three: sigma yy, sigma yx, and sigma yz, and then three for this one, sigma zz, because the force acting on this area, in the z area, if z, and the area is del az, so that will be sigma zz, and then the force which acting in this direction but az, okay, the force will be fx and az. Now the area will be changed, so it will be tau zx and tau zy. So 3 plus 3 plus 3, 9 stresses will be produced. Okay, 3 are normal stresses which are on the main principal diagonal, and the other 6 are the tangential stresses. If we combine all these stresses, we denote all the 9 stresses from this T capital. This is maybe sometime bold. I have shown this from the double lines, double bar, because of to differentiate, because you can see this is stress. Okay, so stresses, it would be better to define to differentiate stresses from scalar and vector. So that's why I have put two lines, okay, in the superscript. Where T is, what is T, which is the representation of all the 9 stresses, is the Cauchy stress tensor. We call this Cauchy stress tensor. Sigma has been used to denote the normal stress, and tau to denote the shear stress or tangential stresses. The notation for design stress is shown in figure 3, which is you can see the 9 stresses. Okay, this is the x surface, this is the y, positive y, and this is the positive z surface. Okay, this one. Sigma zz, tau zx, tau zy. Sorry, this one, sigma zz, tau zx, tau zy. Okay, okay, and you can see the others. For example, this is the right and this is the left. So we don't look at this is the opposite, in the opposite direction. This is the same x plane, but this is the negative plane, x. Positive x plane, negative x. Left, right, this is left. This is top, this is bottom. This is front and this is back. Look at this back. Okay, this is top, this is bottom. This is right, this is left. This is front, this is back. So you can see we have just considered the three mutually perpendicular surfaces. This one, and this one. 3 perpendicular surfaces, and which consist of 9 stresses. Referring to the infinitesimal element shown in figure 3, we see that there are 6 planes. 2 x planes, 2 y planes, and 2 z planes on which stresses may act. In order to designate the plane of interest, we could use terms like front and back, top and bottom, or left and right. I have already discussed this. So, however, it is more logical to name the planes in terms of coordinate axes. The plane are named and denoted as a positive or negative according to the direction of the outwardly drawn normal to the plane. Okay, so when the outward normal is in the x direction, in the x plane, okay, so we call this the positive plane, and you can see when it is in the negative x direction, so it will be considered as negative plane. Okay, so the planes are named and as denoted as positive or negative according to the direction of the outward normal to the plane. Thus, the top plane, for example, is a positive y plane, and the back plane is a negative z plane. It is also necessary to adopt sign convention for stresses. A stress component is positive. Remember, this is very important. A stress will be positive when the direction of the stress component and the plane on which it acts are both positive or both negative. So, if the plane is positive and the direction is also in the positive x direction, so that will be positive. Or the plane is negative and also the direction is negative, then again the stress will be positive. For example, if we have this as a tangential stress in y plane in x direction is 5 lb per feet square, okay, this is pound, represent a shear stress on a positive y plane but in the positive x direction, or a shear stress or negative y plane in the negative x direction. So negative multiply negative become positive. In figure 3, all the stresses have been drawn as a positive stresses. We have not considered because then there will be again 9 stresses, negative stresses. So we have already considered the positive stresses. Stress components are negative when the direction of the stress component and the plane on which it acts are opposite sign. For example, the plane is negative but it is acting in the positive x direction. So the plane is negative, the direction is positive. The plane is positive, the direction is negative. So the result will be negative stress. I hope you will understand this. Okay. So now, uh, as we have discussed the stresses, the 9 stresses, so now I'm going to derive the momentum equation for any fluid. The momentum equation for any fluid, and you can use these length. Okay, so we will use second law of motion, F is equal to ma, and that force F, as we have discussed in this lecture, that that force will be considered as a surface force plus body force, and these forces will generate the stresses, because force per unit area actually is nothing but it develops stresses. Okay, and we have shown that 9 stresses may be developed. Okay, so uh, and in this we will able after the end, after this lecture, that we will have a momentum equation for the for any fluid means for any fluid means that for Newtonian or non-Newtonian, and then in Newtonian non-Newtonian we have time dependent or time independent, or fluid which are shear thinning or shear thickening. Okay, so a dynamic equation describing fluid motion may be obtained. So because we study the fluid in a motion, we study the fluid dynamics. So we will study the fluid in motion, and when the fluid is in motion, so the forces will be applied, okay, on these fluid particles. And as we consider the fluid in continuum, we are not considering individuality, okay. As we have already discussed that individuality, it means that for every and each particle you will be apply second law of motion. So for even in a dot there are million of particles, so you will need million of the Newton second law. If one is equal to ma, if two, if three, and millions, so humanly it is not possible. So that's why we move towards the continuum approach, not collectivity. Collective nature of the fluid. So uh, for the fluid motion may be obtained by applying Newton's second law of motion to a particles. How to derive the equation of describing the fluid motion? So that can be derived while using the Newton's second law of motion. To derive the differential form of momentum equation, we shall apply Newton's second law to an infinitesimal fluid particle having mass dm. So it is an infinitesimal fluid particle, very small fluid particles having mass dm. Recall that the Newton's second law for a finite system is given by F is equal to ma or F is equal to dt in, in terms of the linear momentum. Okay, that in linear momentum, the second law can be defined as the rate of change of the linear momentum. The force is directly proportional to the rate of change of the linear momentum, where p of the system is given by, where the linear momentum p of the system is given by. And now look at this one, this p we call the system. Okay, so as we have shown this, the system approach and the control volume approach. So this is the Lagrangian approach. System approach is the Lagrangian. Lagrangian means when you are studying the individual particle. We have already discussed this in the previous lectures, that Lagrangian approach is actually a system approach in which we study the individual particles, and as all the laws are given in the Lagrangian approach, so we have to translate this, to change this Lagrangian or system approach to the control volume approach. Okay, first we look at this one. Now you can see the volume, the P system, and how to change this to the mass. Okay, so it becomes rho is equal to dV. Okay, so what is dm actually? Mass, okay, which is equal to rho dV. So system or mass, which you can see we have shown this from dm. So P is equal to mv. So this is big, as we have considered very infinitesimal small mass, so that's why we have considered dm. This is very infinitesimal mass. So dmv, mass multiply velocity, is called the linear momentum. Then for the, now we have to replace this p value in this equation. So you can see this is very small force df is equal to dm dv by dt. P has been replaced by this one. So as dm is constant in this case, so we have considered as dv by dt. Okay. Having obtained an expression for the acceleration of a fluid in the middle of the fluid, having obtained an acceleration, look at this one, this is acceleration, rate of change of velocity, this is acceleration. We call this the total acceleration of a fluid element of mass dm. What will be the acceleration of this particle, of the fluid particle or the fluid element having mass dm? The mass of the fluid particle or the fluid element is dm, so what will be its acceleration? Moving in a velocity field. When it is moving in a velocity field, so what will be? Its velocity will be changing. So what will be its acceleration? We can write the Newton's second law as the vector equation F is equal to, we call this ma. So this is m, this is dv by dt is a, or very small force df is equal to dm dv by dt. So I can write this total derivative as a sum of the local derivative, or in other words, the Lagrangian approach is translated to the volume approach or the Eulerian approach. So now you can see this is actually when you are studying something at a point, and this is something you are when you are studying individuality, individual particle, and this shows that something when you are studying something in a region at a point, don't care about the molecules, individual molecule, but you are studying something in a region or on a point. So we call this the Eulerian approach. This is called the Lagrangian approach. So the total derivative or the total acceleration has been changed, translated to, transferred to local acceleration and convective acceleration. Look at this one, how it is changed. You can see local acceleration, this one, this is the convective acceleration, and in the previous lecture we have derived this one, because this is nothing, this is dx by dt, dx by dt, and dt by dx, so it becomes partial v by partial x, okay, and dx by dt is equal to u, and this is dy by dt is equal to v, and dw by, so by dw by dz by dt is equal to w. Okay, so this is called, okay, this one, this is called the, from here to here, this is called convective acceleration. This one is called the local acceleration. So how to find the total acceleration? The total acceleration, which is denoted by d by dt, can be obtained from the local derivative, local acceleration plus the convective acceleration. And we call this as a material derivative or substantial derivative, and this is called the local or convective derivative. Okay, so remember, without this thing, this is mass, we call this one is equal to this thing, because it is, look, you can see this is the same here, but we have split this one into local acceleration and convective acceleration. We now need to obtain a suitable formulation for the force df or its components dfx, dfy and dfz, because the force will acting in x direction, the force will be acting in y direction, the force will be acting in z direction, and at the same time, remember, this is the surface force, but sorry, this is the total force, and the total force may be surface force will be acting on the fluid particle plus some body forces will also acting on the fluid particle. The forces acting on a fluid element may be classified as body forces and surface forces. Surface forces include both normal forces and tangential forces. We shall consider the x component of the force acting on a differential element of mass dm and volume dv, which may be equal to dx dy dz. I have shown this volume from dv. Okay, so this is not v. Okay, this is volume, very small volume. So we shall consider the x component of the force acting on the differential element. Okay, so we will calculate only for in the x direction, and then we will consider also for the similarly we will consider for the y and z direction. Okay. Okay. So now this is very important. Now, if the stresses at the center of the differential elements are taken to be sigma xx, tau x, and tau zx, the center of differential element, then the stresses acting in the x direction on all faces of the element obtained by Taylor series expansion about the center of the element are shown in figure 1. So look at this one now. Okay, uh, this is the center of the fluid element. Okay, this is the differential fluid element. We have considered this uh, cube as a differential fluid element. This is nothing but this is the fluid element. Okay, this is now the fluid element. A differential fluid element okay, so this is the differential fluid element. Okay, so this is now in x direction, z direction, this is x direction, and this is y direction, and this is z direction. Okay, and this is x direction. So the fluid elements, we will discuss the fluid element at the center. So the stresses which is produces at this direction, okay, here, so that will be this at this surface there will be sigma xx, tau xy, tau zx, sorry xz. At this there will be sigma yy, tau yx, and tau yz, and at this there will be sigma zz, sigma zx, and sigma zy. Okay, so we will discuss all these forces at the center of these fluid element. So it is already shown from this figure. Now these are the forces, sigma xx, tau x. These are the forces, sigma yy, you can see sigma yz and sigma yz, y plane in z direction. Similarly, z plane in y direction, z plane in x direction, and z plane in z direction, sigma zz. Okay, so 6 faces of infinitesimal cube, but we only needs the 9, okay, stresses. Okay, so how this come, the forces, look at here from this diagram. Okay, so as we are studying this in the center of the fluid element, so okay, so in the positive explain how to obtain this one. Okay, so let me write, this is very important now. okay, the fluid element in x direction. If you consider this is the x direction, okay, so sorry, this one, okay, so uh, the 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 stresses, the changes will occur in the stresses, okay. So you can see if there is sigma x axis, so sigma x sigma x, and this is the center of x plus dx by 2. So what will be the result on the positive x-axis? Okay, apply the Taylor series x plus dx. Look at this is just the example. So what will be x plus dx is equal to f of x, okay, and plus f dash of x dx 1 factorial, and plus f double dash of x, dx whole square divided by 2 factorial. So this is the Taylor series. So look at this one, the same procedure we will apply. F of x means sigma x axis is the function of x plus partial by sigma dash x means partial by partial x, because the plane is x, so we will use, it will be the changes will be with respect to x plane, this plane, okay. Sigma xx dx plus partial square by partial x square double derivative of sigma xx dx, yeah, it is dx by 2 because we have considered the center. So dx by 2 from this direction and dx by 2, so it becomes dx, okay, because now you can see this. Let me just change it, because we will consider the vertical plates. So let this is the x direction, this is y direction, and this is z direction. So what, look at this one, this will be, this is parallel to okay, this is parallel to y, okay, so this will be dy, and this is parallel to x direction, so this is dx, okay, sorry, this is parallel to z direction, so this is dz, and this is parallel to y, z, so this is dz, sorry, dx, because this is, okay, sorry, this is parallel to this one, okay, this one, and this one, so this is dy, and this one is parallel to x direction, so this is dx. Okay, so look at this one, this is dy, this is dz, and this is dx, okay. So we have considered this is dx, but we have considered this position, the whole is dx, but this is actually, now the distance is dx by 2, this distance is dx by 2. For example, look at this distance, from here to here, this is dx by 2. The center is dx by 2, and this distance is also dx by 2. So dx by 2 plus dx by 2 becomes dx only. So it will become like this. Okay, so as dx by 2, as dx means a very infinitesimal distance. So when we take the square of the infinity, very small, this very small quantity, so the square will becomes more. Okay, it will becomes less than 1. So that's why we ignores the others. We ignores the second order and also the high orders. Okay, and just we'll take these two terms. So how these, that is the explanation that how these two terms comes actually. Okay, like you can see, like this is the positive x surface, sigma x-axis partial by partial x, sigma x-axis dx by 2. So we applied actually the Taylor series, and now this is the x plane, the negative x plane. So in the negative x plane we will just change this. On the negative x plane we will change, sorry, this is x-axis, we will change this into, sorry, x minus dx by 2. Minus dx by 2. So when we change, again, look, you can see it will become sigma xx by using Taylor series. While studying something at the center, so you can apply the about this point, so you can apply this Taylor series, plus partial by partial x into minus dx by 2. And we ignore the other terms because of dx square, dx cube. So you can see this minus will come here. So it will become sigma xx minus partial by partial x sigma xx. So you can see here minus partial by partial x dx by 2. And I can also explain this by another formula, that how the changes occur when something is passing, when something is entering this and outing this. This is in and this is out. So let me explain this again. This from another formula. Look at this one. If you have, this is, look at this one. This is something is entered. Let this y is enter. Or let me write sigma x-axis. Here sigma xx dx. Sigma xx. Sigma xx is at this point A. It enters this point and then it comes to this point. So what changes will be occur? Okay, what changes will be occur? So the formula is, and it covers this distance. This distance. Let's say this distance is dx. Like in our case, this is dx by 2. But let's say I have just considered this distance is. So when it reached to this point from A to B, when it enters A and reach to B, it will cover this distance. So what will be the value? What changes will be occur at point B? So it will be sigma xx changes partial by partial x, because it is with respect to x-axis, and this value sigma x-axis into the distance covered. So the distance is dx. So you can also apply this formula. Okay, that if something is entering or it's moving from this point to this point, so what changes will be occur? So that will be the same, this thing plus the changes in with respect to x in this point, in this value, and the distance covered, that is dx. So now if you take dx by 2, so then will come dx by 2. Okay, so now uh, the stresses in the positive x-axis and the stresses in the negative. So what will be the net stresses in this in the x surface? Because in x surface we have positive x and negative x. So what will be the net? The net will be when we add these two, or when the when sometimes we say that out minus n. Okay, so you can see what will be the net force in the x direction, because it is the in the x direction. So because we have considered all the forces in x direction. So uh, in this plane we will have the forces in x direction, but also in this plane we will have the forces in x direction. Okay, and also in this case we will have the forces in x direction. Okay, like now we can replace this by the plane is now here x, but now the plane will be changed. Look at this one, now the plane will be changed to y, and but in the x direction, and the distance which will be curved will be, the changes will becomes with respect to y axis now, because the plane is now y. Okay, so this will be now changed to dy. And look at this was when this will be changed to tau yx by the green. Look at the green now. Tau yx y plane. The changes will be with respect to y, in this value, which is the same tau yx, and the distance covered is now dy. Okay, so we have three surfaces, and in each surfaces we will take only those stresses which acting on the in the x direction. So now there is a positive y, and we have the forces in x direction, but also we have the negative y surface, and also we will have the forces in the x direction. So now all the forces, the surface forces in x direction, like the one I have found, this one. Okay, and dy by dz. Okay, how it comes now? Look at this one. In this direction we have, this is the x plane, and this is the x direction also. Okay, just not like I have shown. Okay, not okay. So now look at this one. When it is moving, when it is passing through the area, so what will that area will be? Or maybe if I have, if I can show this one, if there is any dy dx. Okay, so look at this one. Your this area is dx. Okay, the distance come when something enters here and comes here. Okay, in this direction, so it will cover this distance. So this will be dx, and this is dz. Okay, so this will be, this is parallel to this one. Okay, so if, let me try to draw again. and very quickly I will try to finish this lecture. So let me draw this again, and very roughly I have made this cube. And look at this one. This is your x direction, okay, and this is your y direction, and this is your z direction. So look at this one. When something enter this area, okay, something, you are studying something and it will out from this area, enter and out, or you are studying the stresses at this positive x-axis. So what will happen actually? Okay, so look at this one. Look at this one. This is the same parallel to this line, so this will be dx. This will be your, look at, this is parallel to this one, so this is dz, and this is parallel to y-axis, this one, so this is dy. Okay, so now look at this area. Look at this area. Look at this. Sorry, I have this area. I have to share this with some other color. So if you look at this area is made of this one and this one. So look at this area. When something is penetrating with this area, so this area is made up of dz, okay, which is equal to this one. Look at this one, and this one, which is dy. So this is the area where it is penetrating, when it is passing through, and which amount is passing through this area. This amount is passing through this area. This is the cross-sectional area, this one. When something is going in x direction, so it will be penetrating, or the cross-section area will be dy by dz. If it is in the y direction, so the penetrating or the cross-sectional area will be dx and dz. If it is in the z direction, so the cross-sectional area will be dx and dy. Okay, remember this. Okay, so now as this is the x plane in x direction, and this is in the y plane in the x direction, plane is y. Okay, so it is entering in the area, but in the x direction. The direction is x, but the y plane. Okay, like now you can see this one. Look at the stresses. This one, this stresses. Okay, in the x direction. So when it is moving in the x direction and the plane is y, the plane is y. Okay, this is the y plane. Okay, this one and this one. So look at the area which is it penetrates. So it is made up of, look at this area. Look at this whole area. This one, this one, this one, and this one. Look at. So it is made up of dx dz, but it is in the x direction. But now in the y plane. Okay, in the y plane and in the x direction, so you can see the cross-sectional area. Okay, so this is the y plane, because they are the same. This is the positive x plane and this is the negative x plane. And look at this one, because it is the outward normal, so we will the positive x plane minus the negative plane, so that will be the net stresses on the x plane, on this plane. Okay, on this x plane, both x plane. This is the positive and this is the negative. So it is the outward normal, so we will uh, this minus this thing. You can see here. This is out minus. So you can see the net will be in this position. Okay, because it is the outward normal. So it is the outward normal is opposite to the direction of the fluid, so it will become minus. So this minus this. This is it will give the net stresses on the x plane in the x direction. And look at this one, dx dz, as I have shown the y plane. This is the y plane in the y plane in the x direction. So you can see, look at this plane. So this cross section becomes of dx and dz, dx and dz. Okay, so y, positive y plane and negative y plane. So you can see in the positive y plane, because okay, y plane in x direction. Okay, so it is on the positive y plane, and the negative y plane there will be negative. Okay, but as it is in the opposite to the outward normal, the outward normal is in the opposite direction of the stresses direction, so that's why we will have minus. So this will be minus. So this will be the net stresses in the x direction on the y plane. Okay, so we have 6 surfaces. 1, 2. This is positive x surface, this is negative x surface. This is positive y surface, this is negative y surface. Now similarly, this is the positive x surface. And look at the stresses in the x direction. Okay, because the plane is y and direction is x, so all the stresses will be tangential, not normal. And look at this one, the surface is x and the direction is x, so you can see these are the normal stresses. Okay, so now again the stresses on the z plane in this direction, and this is the stresses inside the bracket, the stresses on the negative z plane in the x direction. And now we will subtract this from this one, and you can see this will be cancelled with each other, sigma x minus sigma x, and plus partial sigma x, sigma partial by partial x sigma x, and minus positive part to 2 times this one, and dx by 2 plus dx by 2, 2 times dx by 2. So we can take this way. Let me calculate 1, and then you will. So we will have sigma x minus sigma x. So it will cancel each other. Okay, like you can see here, sigma x minus sigma x, plus and minus into minus plus. So 2 times this. So 2 times plus 2 times partial by partial x sigma x into dx by 2. So this 2 will be cancelled with this 2, and just we will have partial by partial x sigma x, and multiply the penetrating area or the cross section area in the dx means dy dz. So now it will becomes the result will be 2 cancel, and just we will have partial by partial x sigma x dx dy and dz. Okay, this comes from this one, and from this one again tau yx will be cancelled with minus tau yx, and just we will have 2 times this thing and divided by 2. So just we will have partial t by partial y and dx dy dz again, and similarly partial by partial z t tau zx dx dy dz. Only the stresses in the x direction, so it becomes like partial by partial x sigma x plus partial by partial y tau ix plus partial by partial z tau zx dz by sorry, this is the mistake. Okay, so let me, I can delete this. Okay, now at the same time, you can see now. So I have partial by partial x sigma x because in all these three we have dx, dy, dz. We have dx, dy, dz. Also, we have from this dx, dy, dz. Also, we have dx, dy, dz. And we will take it common from all these three. And we have from the first one, from this one, we only have only left partial by partial x sigma xx. From this one, we only left partial by partial y tau yx. From this one, we only left partial by partial z tau zx in the x direction. You can see. Okay, so all, as I have mentioned this, that this is only the surface force, but also we will have the body force in the x direction, because I am discussing this in the components form: x direction, y direction, and z direction. When the forces of gravity is the only body force acting, then the body force per unit mass is g. The net force in the x direction, dfx, is given by rho gx. What is this rho gx? This is the body force and this is the surface force. Body force plus surface force. So remember that these things comes from the body, the surface forces, this portion, and this portion comes from the body force. Similarly, we can do the dfy, which will be equal to df, body force in y direction, and surface forces in y direction, and that will be rho gy partial by partial y sigma yy partial by partial x ta xy. Those forces on the x plane in y direction, and the force is partial by partial z, but this will be changed into y, sorry, z plane in y direction. This will be becomes y. Okay, and this is again mistake. So let me again delete this. Typo mistake. Okay. So similarly in the z direction, this will be changed to rho gz. Okay, there is no arrow. Okay, remember there is no arrow, because on the arrow should be deleted, because it is only exponent form in this direction. So if you can, okay, we will remove this from all these. So rho gz partial by partial z sigma zz partial by partial x tau xz, explained in z direction. All the forces, stresses in the z direction. So plane is x. We will have plane is x, but in the z direction. Already explained this. Partial by partial y, plane is y, but in the z direction. When we combine all these things, look at this one. This is forces in the y direction. Okay, I have just calculate in detail. You can do like this. You can derive all the forces in detail in the y direction also by referencing this table. Okay, now look at this one. In the y direction, all the forces, look at, in the x plane we will consider this one x plane in y direction, but here y plane in y direction, but in z plane and in y direction. So we will calculate all these forces. Similarly, then in the x plane in z direction, all the stresses, and in the y plane in z direction, and in the z plane in z direction. So that will be normal stresses. Okay, so you can see I have just similarly, to save the time, we have just shown directly, keep in mind the above process, the force in y direction, surface force in y. So this should be y, okay? This should be y and this should be z. Okay, gy and gz. So now, sorry, okay, we have now formulated expression for the components dfx, dfy, all the forces, the sum of all the forces, meaning in the x direction. There is no need to put the arrows here. This should be removed. This should be removed. This should be removed. Okay, and the force is in x direction. So now this is no more vector. This is no more vector, and this is no more vector. Okay, so the surface forces plus the body forces in a direction. Fy shows the surface forces, the body forces in y direction, and the surface forces and body forces in z directions. Okay, acting on the fluid element of mass dm, having mass dm. These are the fluid. These are the forces which acting on the fluid element having mass dm. If we substitute this expression in equation 6 to 9 for the force component into the x, y, and z components of equation 4, so look at equation 4. Look at this one. Now we will uh, change this into the components form. Okay, equation 4. But now if this is the in the fx, so fx, for fx we will have the velocity component, the x will be u, so it will be replaced by u. Only the vectors v will be changed to u, and for the fy, this v will be changed to v, this small, okay, component v, component v, component v, component v, component v. For the dfz, this v will be changed to dw dt, and this will be changed to partial w by partial t, partial w by partial x, partial w by partial y, partial w by partial z. Okay, so you can see in equation 4 we obtain the different equation of the motion rho dv. This is the dv, dx, dy, dz, because dm has been changed to rho dv. Mass is changed to, what is mass? Huh? So mass is equal to rho dv, while u multiply rho. And look at this one, partial u by partial t. I have already explained this, that v vector will be changed to x component of velocity is u, and the x component of the stresses plus the body force. Okay, I have, yeah, here I have mentioned this partial by partial x sigma axis. So these are all the stresses, the surface forces plus the body forces in x direction, and this is the velocity in x direction. Similarly, this is the velocity in the y direction, the acceleration in the y direction, and these are the forces in the y direction, body force plus surface forces. Okay, and look at this one, the acceleration, when you apply the force on the mass and it is moving in the z direction, so the fluid particles, the forces, the surface forces which will be generated in the z direction are, look at this one, z, 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 z shows the direction, and these are the body forces which may be applied in the z direction. So you can see 9, 10, 11. Okay, equation 9 to 11 are the differential equation of motion for any fluid satisfying the continuum assumptions in the component form. Before the equation can be used to solve u, v, and w, suitable expression for the stress must be obtained in terms of the velocity and pressure field in vector form. Equation 9 to 11 can be expressed now in the vectorial form, because normally we will use this, because this is the extra. I have repeat this one here because there is no given the body force. So we are have 9, 10, 11. So look at this one. Look at this one. U, V, W. So it will becomes V. Okay. Partial by partial x, partial by partial y, partial by partial z. It will become divergence, nebula. Okay, and sigma xx, tau yx, and tau zx. So these are the 9 stresses, and we have already shown these 9 stresses from the t. So rho dv by dt. So it becomes rho, and u v w by becomes v vector, and the 9 stresses, sigma xx, sigma yy, sigma zz, and tau xy, tau yx, it becomes t. So and partial by partial x, partial by partial y, partial by partial z becomes divergence, nebula. This is nebula, okay? This is operator nebula. Maybe this is just like nebula. I can show this divergence as uh, okay, as this divergence. So I can write control F, um, partial by partial, mm, partial by x plus and I. Okay, sometimes when you in projector form, maybe I, J, and K. So control C, control V, control V. So partial by partial Y, and let me write here. Okay, sorry. Control bracket. This is some dot, maybe something. Any properties, dot. Control C, control V, control V, Z equal to divergence. Divergence of dot. Okay, sorry, dot. And this is maybe sometime we write this as a nebula. Where is nebula? Yeah, this one. And we use here dot. We use dot. This one. Nebula dot. Okay, so divergence and this. So maybe sometime we write like this. Okay, so not we don't need this one. Okay, so I have to. Okay, let me. Okay, so I just for explanation. So a divergence of t, and what is t? This is sigma x is this thing. Okay, so equation 12 is the momentum equation in vector form for any fluid. So this is the end of this lecture. Okay, and this Cauchy stressor may be, and this is not a vector. Okay, this may be vector. I already defined this from the double dot. Okay, so maybe we can define this r bold. Let me do this, or there should be double dot, because vector should be differentiate from the, I don't know where is the, what is this, yeah, so this should be okay, double dot. So similarly this t should be like this. Okay, no need to write. Okay, the, there should be double dot 1, and again this is, sorry, please adding 5 exact. Okay, you can see now this, what mean double dot means this is tensor, this is not vector. Vector is expressed from the arrow, and scalar is without normal, and tensor is from the double subscript, okay, superscript, double line in the superscript. Okay, so this may be for any fluid. So for example, if you want to this is when the fluid is moving, okay, so this is the momentum equation, and this can be specified for a special fluid like Navier-Stokes equation or for the Newtonian fluid. So this can be defined for the Navier-Stokes equation or for the Newtonian fluid. For the second grade fluid, it will have some other shape. Okay, it can be defined in some other way. For the Kessel fluid, it may be defined in some other way. So, but the vectorial form is that just the governing equation for the different fluids can be described, can be derived while only changing this t. Okay, this t will be different for different fluids. So now you are able, you have derived this this equation, okay, for any fluids, and for the specific fluid we will define this tau, and then we will derive the governing equation for that fluid, like second grade fluid, Newtonian fluid, Jeffrey fluid, Maxwell fluid. Okay, so and this is the end of this lecture, but actually in the assignment you have to provide it, you have to provide in detail these y components. Okay, these two, how to get these two while calculating, just like I have calculated for the x, for the all the stresses in the x direction. Okay, I also, in that will be the part of the minor weekly assignment. Okay, so this is the end of this lecture, and again, if you have any ambiguity in this lecture, any problem in this lecture, so you can come. Okay, as we have scheduled, as we have already a display and share the meeting time, so you can come and discuss with me. Okay, I will derive this one for you again. Okay, if you have any ambiguity uh, in the stresses or in this equation especially. Okay, this equation, this is come from the acceleration part, particularly this is very important. This is for every fluid you will have, for the unsteady fluid you will have this part, but this part, because the stresses when applied, the fluid is moving, so the stresses will be produced, and this will be this will be different. Okay, for for every fluid. Okay, so this is the end of this lecture. Thank you very much.